Alright, boys and girls, welcome back to the drive-through. As we go into some arc length review, and then more importantly, some angular and linear velocity stuff. Let's just talk about arc length in terms of a central angle for right now. If we have some angle theta and of a circle, and we have some radius r, how can we find out the length of that red arc? Well, if this angle is theta, then that arc is also theta, same measure degrees from geometry. So you figure out what portion out of 360 is that arc. That gives you the fraction of the circle represented by the pathway taken on the arc, and then you just multiply by 2 pi r, which is your circumference, and that is your arc length, L. They also call that S sometimes. Okay? So, it's really advantageous to work in radians, because another way to find S is just to take theta in radians and multiply it by r. Okay, so let's just do an example to make sure you guys understand what that is. Let's say that theta is 60 and r is 10. So the circumference of this circle would be 2 times pi times r, so 20 times pi. Okay, so the arc length, which we are from here on out going to call S, is, in degrees, we would do 60 over 360 times 20 pi, okay, which is, let's see, 60 times 20 is 1200 pi divided by 360. Let's see, so that is, well, 120 pi over 36, which is divide everything by, let's just divide everything by 12, so that's 10 pi over 3. Okay, now in radians, to find the arc length, which we're now going to call S, how many radians is 60 degrees? Well, that's pi over 3 radians. Okay, so it's pi over 3 times the radius, 10. Aha, that is much easier. So as you can see, when we're dealing with arc length, it's really a lot easier to deal with radians. So remember, to find the arc length, it's just the radians times the radius. So, now, let's think about linear and angular velocity. I want you to think that, well, first I want you to understand that in physics, things spin around in circles all the time. Wheels, planets, pulleys, I don't know, all sorts of things just spin. Engines. Okay? So, there's two different ways to measure this speed. Linear velocity is found by taking distance and divided by time. The units is miles per hour, or miles per hour, or meters per second, or kilometers per hour. Okay, those are all different ways to measure velocity that you're familiar with. Okay, now I'm going to come back up and give you some more velocity equations. Okay, but angular velocity, and typically velocity, the variable is v. Angular velocity, the variable is w. And w is defined to be the radians divided by the time. Okay? And the key thing that I want you to understand, like this is definitely the most important part of this chapter, of this section I should say, if you had a pole that was green, and that pole was spinning around and creating this pathway that I drew before, okay? I want you to understand that if there was a bug here on that pole, a red bug, and there was a black bug here on that pole, the black bug would be traveling at a much higher velocity than the red bug. That's very important for you to understand. If this green stick was traveling around, acting as a radius, you could imagine that this loop, it would take the same amount of time, okay, for this black bug to complete a full loop as it would for the red bug to complete a full loop. However, the black bug would have traveled a significantly more distance, but they both traveled the same amount of radians. So, angular velocity and velocity are very different, and that's what I want you to understand about this concept, okay? Now, as far as velocity goes, we just learned that distance could also be expressed as a length. So we could also say that velocity is s over t. Okay? However, we just learned that, if you look at our previous slide, s is theta times r. It's the radians times the radius. So we could also say that it's radians times radius divided by t. Well, hold on a second. Look at this. It's the same as that. So you could also say that linear velocity is the angular velocity times the radius. Okay? So these are all equations you're going to use. And so you're going to want to have a list of them. And how quickly you're able to do this really depends on which equation you use. So let's get started. A belt runs a pulley of, this should be of radius 6 centimeters. Oh, hold on a sec. Okay, I cleaned up the problem. A belt runs a pulley of radius 6 centimeters at 80 revolutions per second. So that means we got 6 centimeters, and for each second, this thing revolves 80 times. So it is spinning super fast, okay? Find the angular velocity in radians per second. That's important. So, how many radians are there per second? Well, there's 2 pi radians in 1 revolution, and we are going 80 revolutions per second. Okay, so this is just, hey Carson, what's this called when we do this? Yeah, but what's that called in science? No, never mind. It's got like a term. You haven't gotten to it yet. But Mrs. Villardo is going to tell me. So, the revolutions cancel, and now we've got 160 pi radians per second. That is your angular velocity, okay? What's the linear velocity? Let's go back and look for the best equation we could use. Well, I think we just want to use this. Okay? Let's use our angular velocity and multiply it by our radius. So, our velocity is going to be 160 pi radians per 1 second times 6 centimeters. Okay? And when you do 160 times 6, second quick, come on. Let me pause. 160 times 6 times pi. Let's not put pi in our answer if we're talking about a velocity, because we want to get a good idea how fast this thing is moving. Oh my gosh. There's pi. Sorry. And you get 3015.9 centimeters per second. Okay? Now, you might be better off writing that in meters per second. So let's see. Let's see how you do this. 3015.9 centimeters in 1 second times, let's see, 1 meter has 100 centimeters. Now the centimeters cancel, so if I divide that by 100, it's 30.15 meters per second. So that's moving. It's like almost 100 yards a second. Okay? Hope that helps. Let's do another one. A satellite is traveling in a circular orbit 1,600 kilometers above the surface of the Earth. It takes 2 hours to make an orbit. Find the linear velocity of the satellite. All right, so velocity here is distance divided by time. We know that the time is 2 hours. Okay, we need to find the distance. Well, to find the distance, we need to find the circumference. It's 2 times pi times r, so it's 2 times pi. Jeez, Pete's. Sorry, ViewSonic. 2 times pi. It says assume times. All right, now what we have here is the Earth. Well, let's not make the Earth in red yet. It's not yet on fire. Here's the Earth. This is 6,400. But here is the satellite. Okay, and that is an additional 1,600. And there's the path that the satellite's taking. So what is the radius of the satellite? It's 6,400 plus 1,600. It's 8,000. Okay? So 16,000 times pi, 2 times 8,000 times pi. Oh gosh, I hate this thing. 2, so 16,000 times pi, and you get 50265.5. $50265.5. Okay, so that's the distance. Now I got to include my units, so that is kilometers. So I got to do that divided by 2. So you get 25,000 132.7 kilometers per hour. Okay, so how far does it travel? travel in 4.5 hours? Well, if it travels 25,132.7 kilometers in 1 hour times 4 hours, hours cancel. Now that's going to give you kilometers for your answer. That's what you want. Factor labeling, I believe, is what this is called. So just take my answer, multiply it by 4.5, and you get 11,397 kilometers. Which makes sense. That's a little bit more than 2 orbits. I hope this helps. We're going to get you some extra practice, and then you're going to come up with a question on your own. Your formative assessment is going to be a riot for this. Boom!